Okay, guys, we were to discuss polyhalogens. This is the last part of alkyl halides and aryl halides. So let's look into this. We have various polyhalides starting from CH, CH2, Cl2 or X2. We write down this as X2 and CH, X3 and CX4. These are the polyhalogens. Okay. We can also have polyhalogens in the form of X and X dash. We can have X2 and X dash, or we can have X3 and X dash. These are also polyhalogens. Okay, uh, interpolyhalogens. Interpolyhalogens. Got it. The first which is most important, generally used is CH2, Cl2, which is dichloro, dichloromethane. Okay, this is an important polyhalogen. If you notice the preparation wise, got it? 1 second. Sorry, please check. Preparation wise, if you notice, is about CHCl3, that is chloroform. When you treat with iron and H2O, that will convert into CH2, Cl2. Other alternative reagents that we can use is Zn in the presence of HCl. Okay, limited. So if you have limited amount, so that will convert into CH2, Cl2. So this is the type of preparation which you will notice. Got it? Uh, Property wise, if you notice, this is basically a polar aprotic solvent used mainly for used mainly during SN2 and E2 reactions. SN2 and E2 reactions. Got it? Next, if you check out the reactions of uh, dichloromethane, you would see CH2Cl2. This on hydrolysis will replace those two chlorides with OH groups, which will convert into HCHO, so formaldehyde. And this will be more facilitated in acidic medium or either in basic medium. Got it? Mechanism is mostly SN2 driven. Okay, so this is how it will go. Other reactions which you will notice is R CH2Cl2. If you have it like this, then we have H2O in the presence of OH minus will convert into RCHO. Even if you have it on the aryl positions like CH2Cl2, so that on reaction with H2O in the presence of OH minus will convert this into benzaldehyde. This is a typical reactions which you notice for dichloromethane. Got it? The second type of polyhalogens that you will notice will be haloforms. Haloforms. CHF3, CHCl3, CHBr3, and CHI3. These are the four haloforms. This is called fluoroform, chloroform, bromoform, um, iodoform. These are the four types of haloforms that you will get. Okay. You'll notice that CHF3 is basically a colorless gas. CHCl3 is colorless liquid, CHBr3 is also colorless liquid, while this is yellow liquid. Okay, got it. CHCl3 is mainly used for general anesthesia, while chloroform is used as an antiseptic. Okay, these are some basic ideas we should know, that what is the haloforms and what are their basic uses. Now, notice preparation wise. If you notice preparation wise, in case if it is about fluorine, the one way of preparing fluorine is take CF3COOH, react with CaO in the presence of NaOH and heat, which is soda lime decarboxylation. So you'll get CHF3 and carbon dioxide. Okay, so this is for fluoroform. Correct. Next, you will see second reaction is haloform reaction. Haloform haloform reaction is preparation of CHX3, where X could be chlorine, bromine, or iodine. For this, we have very famous reaction, haloform reaction. Got it? Now, haloform reaction can be done either by alcohols, which has a methyl group at the beta position. That is, if this is the alpha position where OH is present, at beta position, we must have an methyl group. So, what are the conditions here? Must have at least one alpha hydrogen and must have methyl at beta carbon. Okay, sorry, or let me put it the other way around. Beta carbon should be methyl. Beta carbon should be methyl form. Okay, so this is the basic idea we should know. Correct. Now, this is with respect to alcohols. Now, if it comes to aldehydes or ketones also, it is the same thing. C double bond O, CH3, or CH3, C double bond OH. So you can see across the alpha position now, you should have, with respect to aldehydes and ketones, this is called alpha position. So this is the must condition. Okay, must have alpha methyl group. This is the condition whenever you have an aldehyde or ketone or alcohol. Okay, correct. Now this R could be alkyl, all aryl will give similar products. So these are few conditions for haloforms. Now let's look into the reaction, how it proceeds. Got it? Let me first write an overall reaction and then we'll see the mechanism also. Overall reaction, if you notice, pH, CHOH and CH3. If you treat this with NaOH and treat with X2, then this will convert into PHCOO minus Na plus, a salt form, and a halo form would be formed. This is the overall reaction. Now let's see how it proceeds. mechanism wise. See, first role is to make sure that we convert this alcohol into aldehyde or ketone. So in the presence of OH minus, we will be able to see this as pH. Able to see this as pH, CHO minus, CH3 here, correct? And H2O. Okay, the equilibrium will mostly be on the left hand side. But the minute an electrophile starts appearing, in this case X2, O minus will start attacking on the electrophile here, removing this X minus. So we will get PH CHOX CH3 plus X minus. Got it? Now, the next step is this hydrogen which is present on the carbon here will have a strong pulling nature by this OX, because of which now the OH minus will try to extract this H plus, which will push this pi bond towards this oxygen. Okay, so first let me put it in terms of intermediate step. I'll tell. I'll go. So then we have pH, then O and X minus with CH3. Wait. Then we will get this as H2. Now, this particular intermediate which is forming, it will push this negative charge here and remove this X minus. And that's how the first thing what you will notice is that it is forming an ketone. So alcohols will also first form ketones. So actually reaction starts from ketones. But why we are doing alcohol, why we are saying alcohols will also give haloform is because the first of this mechanism is related to the oxidation of alcohols. Okay. So let me write down that here. All these steps includes the oxidation of alcohols to aldehydes or ketones. So once you get an oxidation done, from here onwards the haloform reactions begins. That is RC double bond O CH3 will be treated with OH minus. So this will undergo enolization, which means OH minus will attack here. It will try to form an enol here. So I cannot make tea. Okay. So this is CH2 minus, which will be in resonance. It's called. So O minus double bond CH2. So this is enolate ion. Oh. Enolate ion. Okay. The next step is about CO minus double bond CH2 when it reacts with X2. Okay. So O minus will push here. The pi bond will go attack on X. X minus will be relieved. And that will give us R C double bond O CH2X. Okay. So let's say the removal of this OH minus, let's call this at rate R1. Okay. This is happening at rate R1. Okay. So once you get this, what is the first thing we got? Alpha halo, okay, ketones. Alpha halo ketones. Just a second. We got alpha halo ketone. Now, the next step will be even better because this alpha halo ketone will go react with OH minus again. This time, taking H plus will become even more easier. Let's say this is happening at rate R2. Got it? Then we'll get this as RCO minus double bond CH2 plus H2O. Now this would again react with X2. The next mole will react with X2, closing here. This will attack here, X minus, and that will give you RC double bond O CH. There is already X here. CHX2 plus X minus. Okay. And this, if you react with OH minus once again, got it? Let this be rate R3 this time. And this would form RCO minus double bond CX2 plus H2O. And this, when you react with X2 again, okay, so this will be pushed, pi bond will go attack here, X minus will leave, and you will get this as R C double bond O and CX3. Okay, which means till the time you get all the hydrogens replaced by halogen, this reaction would keep proceeding. Okay, and now once you get this form here, you will see R C double bond O CX3. This time when OH minus reacts, it does not have any alternative but to attack as a nucleophile now. So it will attack as a nucleophile. So I will get this as RCO minus with OH and CX3, and which makes CX3 a good leaving group. So it will leave away trying to close the bond. Hence we will get R C double bond OH plus CX3 minus. And CH3 minus is a strong base, takes away H plus from the acid. And that's how eventually we'll get R C double bond O minus plus CHX3. So a haloform formation. Got it? Now let me show you some important aspects here. First thing, check out the number of times we used OH. First, from alcohols onwards, 1 mole here, second mole here. So which means to make the oxidation of these alcohols into ketones, we require these 2 moles of OH minus. And how many moles of X2 we have used? We have used 1 mole of X2. Okay. And now, once it becomes a ketone, then how many moles of OH minus we have used? Check it out. The first mole is here, OH minus. Second mole is OH minus. Third mole is OH minus here, and fourth mole is OH minus here. So in total, we used 4 moles of OH minus. And how many X3 we have used here? X2 we have used here. 1, 2, and 3. 3 moles of X2 we have used. Okay. So during the reactions, this becomes an important part. So when you write the overall reaction, everybody, so see this. I'm writing it as the overall reaction. If you write from the alcohol position, then we actually require, sorry, CH3. We actually require 6 moles of NaOH plus 4 moles of X2 to finally get this into PHCOO minus plus CHX3 plus 6 moles of NaX. Okay, this is what has been formed. Clear? So basically all of these 6 moles here, so this will be 5 moles here, 5. Okay, 5 moles of NaX and PHCO minus Na plus. That is the other Na plus which we will get. So you can see 5 plus 3, 8. 8 of X and 6 of NaOH has been used. In case if you start the reaction with the ketone here, C double bond O as per the question, then you will be using 4 moles of NaOH plus 3 moles of X2, and that would give us PHCOO minus plus CHX3, and then we have 3 moles of NaX. This will be the product form. So depending upon where you start, accordingly you will get the reaction. Now, some important features here that what you need to learn is rate of, you know, enolization. If you compare, see, R1 was slower because you are removing H plus from the CH3. Now R2 will be little faster because having one halogen is a withdrawing group that increases the acidic nature of this hydrogen. And R3 will be even better because when this attacks here, so removing this H plus will become even more faster. So therefore, in this case, R3 is greater than R2 is greater than R1. That will be the rate of enolization form. Okay, got it? That will be the rate of enolization form. And if you have to decide what is the rate determining step here, so basically there are two steps that will compete. One is this one where the OH minus is attacking at the end. The other one is the very first one here. So these two will always compete. So see, rate of haloform, rate of haloform reaction is either formation formation of formation of first enolate ion, or attack of OH minus as nucleophile. These two will complete. But one thing you need to know, that whenever the X is getting attached, that is never a rate determining step. So therefore, rate of therefore rate of halogenation rate of halogenation is same for, you know, is same for chlorine, will be same for bromine, will be same for iodine. So there you will not find any difference between these three. Got it? So rate of reaction will be same for all the cases. I mean all the halogens, whether it is chlorine, bromine, or iodine. Okay. So I want you to have a quick look about it, see how the reaction mechanism works. If there is any doubt, you can ask me now. So see cases where haloform reaction is observed. Okay. So first case, check out if you have CH3 CH2OH. So the requirement is fulfilled. At alpha position, you have at least one hydrogen, and beta position is a methyl group. That's the role. So this is correct. Okay. Now, even if you have CH3 CH2X also, X could be chlorine, bromine, or iodine. Even the halogens will give the similar reaction, as this halogen will first convert into alcohol will then convert into aldehydes. So which means acetaldehyde will also give you positive reaction. And next, if you have any halogen at this position, any alcohol at this position, or ketone at this position, that will also give. Similarly, any halogen like this, any alcohol like this, the same position like this, alcohol, or any form of ketone like this, because as long as there is a methyl available, you can see there is a methyl available, you can get them into haloform formation. Okay. Next, if you already have some halogen, that is like it is in an intermediate step, like we have a ketone here, and then you already have one halogen, or if you have two halogens already, or if you have three halogens already. So they will anyway, they have already made an halogen form on it. So if you add more X2 on it, so that will convert into an halogen form, correct? So wherever you see these kind of forms, whether it is alcohols, aldehydes, ketones, everything, objective is very simple. Locate for the beta CH3 group if it is alcohols. It is alpha CH3 group if it is aldehydes and ketones. Okay. Now, which will not give here, which haloforms, which compounds does not give haloform, does not give haloform reaction. Okay. So check out first CH3, CH3, CH3 and OH, tertiary alcohols. Okay. Or you can have tertiary alkyl halides, tertiary alkyl halides. Because there is no alpha hydrogen, so the one of the important condition is that it has to get oxidized, so it needs to have alpha hydrogen. That alpha hydrogen is not there, or any of these kind of combinations as long as it is tertiary. So which means like this, if you have an alcohol like this, correct, sorry, if you have an alcohol like this, or if you have an alkyl halide like this will not give. Other than that, if you have a ketones which does not have a methyl group, or if you have an aldehyde which does not have an methyl group like this, so they all will not respond. Of course, benzaldehyde and all does not have anything, formaldehyde does not have anything, so these all will not respond to any kind of haloform reaction. Clear? So keep that in mind, these are not for haloforms. Now next thing is about, okay, uh, active methylene, active methylene cases for haloform. So another very important case is that when you have an active methylene stuck between aldehydes or ketones like this, a CH2 group, a CH2 group, and on the left hand side and the right hand side, it should always have an aldehyde or a keto group. Then this would always give you positive, just like this. You can have double bond O, double bond O, H, or you can have like this, double bond O, double bond O. This will also respond. You can have double bond O. You know, alcohol maybe first alcohol will happen to get into an active methylene form, and then you can get the same. So OH and OH like this one. Okay, or you can have OH, double bond OH. So you can notice that these are all the one which I'm marking. These are all, active methylene positions, correct? Another active methylene position which you will see in a ring structure where you will have double bond O, double bond O. So this is also an active methylene. So all of these active methylene groups, active methylene containing groups, they will definitely give you haloform reaction. Now let us see how that is happening here with one example, right? See this example here. Suppose, let's say I have ketone like this on both ends. Now, when you react with NaOH and X2, the first thing you need to notice is to enolize the ketonic positions here. You need to check which one is more acidic hydrogens. And if you compare these these hydrogens and these three hydrogens, you will see, correct, in the sense of acidic nature here, correct, the sense of acidic nature, the hydrogens which are in the pink here, so they will have more acidic nature than these hydrogens. Okay, Because they are active methylene, both sides they are pulled by the double bond O, the carb anion will become stable. That's why NaOH, even though there is a methyl here, it will not go and attack there. It will always try to take H plus from here. And that's the reason why the reaction will proceed to get 2 moles of CH3COO minus plus CHX3. This is the product form. And now let me show you the mechanism how it happens here. Check. So first double bond O, double bond O, and of course there are two hydrogens, active methylene hydrogens here. So OH minus will first definitely take the H plus from here, and that will push into formation of minus charge here, and that will react with X2, correct? And as it reacts with X2, we have already learned that this will go attack on X2, and we will get this as double bond O here, double bond O here like this, and here we'll get X. So you do one more time with NaOH and X2, you will get two halogens getting substituted here. Two halogens getting substituted. Now here is the tricky part. Once you get two halogens on the active methylene position, now that becomes a good leaving group. And that's the reason why OH minus will attack on any one of the carbonyl compound. That means either on C double bond O here or C double bond O here. Any one of them you can attack, and it will go through this formation double bond O, X and X with O minus and OH. Okay. Now as it closes here, this group will break now, because now that CX2 minus is a good leaving group. So that will convert into CX2 minus plus CH3COOH. Okay. And you know that this minus can, once you get that here, it can take H plus from here. It can take H plus from here, or you can continue the reaction. So what is the continuation of the reaction? Is that C double bond O X2 minus can again react with another X2, and this can, sorry, this X minus can attack on X2 here, and that will form C double bond O CX3. And you know that rest is the history. You know what will happen. That is, when you treat this kind with NaOH and OH minus, sorry, NaOH and X2, this will convert into C double bond O minus Na plus plus CHX3. So that's how you'll get the halo form. Now let me mark the carbon to which we are actually making this reaction. This is that carbon which we are talking about. So that is the haloform carbon. Okay. Right. So please do check how the reactions work on active methylene cases, everybody. Have a look. Okay. Cases where active methylene does not give haloform. Does not give haloform. So see the first case. Okay. Suppose if you have active methylene, but on the other end we have something like an ester form, then it will not give. Or hmm, so then we have NO2 here or cyanide here or pH here like this. If you have any of these groups which is withdrawing, correct, double bond O, and here we have maybe Nr2 group here like this. In such cases, although this is an active methylene carbon, these are all active methylene carbons, but and also there is an haloform that, I mean, halogenation happens on that, it eventually does not turn out to be haloform. Let me show you with one example. Example here, you can see, for example, if you take the same ketone here, same ester here with NaOH and X2. So first two moles definitely will go to the active methylene position and get you two halogens here. Later on, when you again treat with OH minus, first of all, the reactivity on this side of it will be very, very less. Why? Most of it get precipitated. Got it? So let me write down that. Most of it gets precipitated. Even if there is something left over, so imagine if this compound is going, we'll get this as O minus, and then we'll get CH2 minus with double bond OOR, and sorry, OH here, correct? And this CX2 minus will take H plus from here, and that will become carboxylate, and it will get precipitated here, CH2X2 C double bond OR, because here OH minus attack will not happen that easily. Hence, this is not a haloform. It will get precipitated here itself. Everybody clear with the problem? So this is a problem. Even after the breaking, you will not get exactly the haloform. You will get some kind of a residual like this. So this kind of residue is not a haloform, neither this kind of a residue is haloform. So if you notice these kind of cases, it will not be giving any haloform reactions. All good, everyone? So I hope you got the basic cases where haloform will occur and where haloform will not be observed. Now, I'll give you some examples. First, please try them. Okay. See what is the product that you're supposed to get. Correct? Just think in terms of haloform reactions only. Okay. So see what are all the cases here. First, OH with NaOI. These are all various ways of representing the haloform. Okay. First case. Second, CH3, CH2OH, the presence of CaOCl2. Next, if you have a double bond OH and then you're treating that with NaOBr. Next, if you are treating with double bond O with NaOH and Cl2. If one side I have an acid, other side I have COOH, and then NaOI, what is the product? Got it? CH triple bond CH connected with C double bond OCH3. This if you react with X2 in the presence of NaOH. Next, if you have double bond O with I2 and NaOH. Okay. If you have Br and Br here in the presence of NaOBr. Okay. Right. So please check this and try to make the product out of it. Everybody. Write all the possible products here. Let's see the answers one by one. First one, count the carbons. 1, 2, 3, 4. 4 carbons. That will become CO minus. Uh, the other carbon should become CHI3. Here, HCO minus, right? Minus as in you can take basically calcium salt, so you can take it as twice calcium, and the other one will be CHCl3. Usually, iodoform is always yellow PPT. Okay, so okay, so you get this as 1 minute. See, so we'll get this as minus. Then we get CHBr3. So it shows that the double bond is not going to get disturbed in the presence of this haloform reaction. Next here we'll get CO minus, COO minus plus 2 moles of CHCl3. Next here acid will not get disturbed, it will become CO minus and CO minus, and the other one becomes CHI3. Next CH triple bond C, which is not here, and this C connects with C double bond O minus plus CHX3. Next, here you can get this active methylene CH3 CO minus plus CHI3, and here we'll get double bond O minus, and then we get CHBr3. Okay, yeah, please check the answers. Done with the haloform. Any doubts here? Right. Let's see. See, generally manufacturing of chloroform, because chloroform has more uses. We'll see more into that. Mainly comes from alcohol, CH3, CH2OH, reacting with bleaching powder. This is the bleach. As you react, you can see haloform reaction will take place here, and you will get chloroform here. This will be HCOO twice calcium. That's how haloforms are being made. Chloroform is being made. Got it? So if you compare the properties of chloroform, basic things which you need to know is it's a colorless liquid, which I think I mentioned it all earlier, and it is a general anesthesia. Okay. It has pleasant smell. It will have pleasant smell, correct? It reacts with it reacts with O2 immediately, correct? In light, reacts with O2 in light to produce a harmful gas known as phosgene. Okay. CHCl3 plus O2, that will become COCl2 plus H2O. Okay. So this is that harmful gas, phosgene. In fact, what we can do, we can prevent that. To prevent phosgene from forming, to prevent phosgene formation. Most of the chloroform, okay, is mixed with, sorry, CHCl3 is mixed with some ethanol, ETOH, ethanol. Okay, so what will ethanol do? Basically, ethanol will try to uh, make a layer of this kind. Correct. So this will be Et2CO2, CO3. Correct. So this will become a soluble, non-toxic carboxylate that will avoid any kind of oxidation with oxygen. Got it? Now, what are all the reactions that you will notice from chloroform here? The first reaction of chloroform is reaction with concentrated HNO3. Concentrated HNO3 will become a uh, uh, source of NO2 plus. Correct. So it will be like we'll be removing out this H plus, and that C minus will be attacking this NO2 plus. So that makes it CNO2 with Cl thrice. CNO2 with Cl thrice. Okay. So this is how the structure would be. O2N, carbon having three chloride groups like this. Got it? This is called nitrochloroform. Nitrochloroform. The common name or industrial name is chloropicrin. This is called chloropicrin. Okay, used as insecticide. Is used as insecticide. Second reaction is CHCl3 reacting with ketone in the presence of OH minus. So basically, first OH minus will take away this H plus, then C minus will go and attack here. So that makes it OH and CCl3. This is the attach. So this is called chloritone. Chloritone. Industrial name is chloritone. Chloritone is an hypnotic drug. Hypnotic drug. Got it? Third reaction is carbyl amine test. Carbyl amine test. Okay. Also known as isocyanate test. Okay. So what would happen here is primary amine when you react with CHCl3 in the presence of KOH, alcoholic, that will convert into RNC, which is isocyanate. Isocyanate formation, which is a foul smelling gas. Foul smelling vapors. So that's kind of confirmation that there is a primary amine present. So it is a detection for primary amine. So it is used as a test for 1 degree amine. Got it? See the mechanism. Learn it here. We don't have to learn it again on amines, okay? Because this is a very repetitive and asked many times in different topics. So check it out. So first we have CHCl3 reacting with OH minus. That will give you CCl3 minus plus H2O. CCl3 is unstable form here. So we will have minus with Cl, Cl and Cl. So that will push the electrons to remove chlorine. So which makes it as CCl2 plus Cl minus. So this is dichlorocarbene. dichlorocarbon is an intermediate which is formed. Okay, and now RNH2 is a good nucleophile which notices that there is an availability of dichlorocarbon here. So immediately the lone pair will go attack on the empty orbitals. Sorry. So as it does, we'll get this as R, N, H and H, then CCl2 minus with plus. And the C minus will take H plus from here, and you'll get this as R, NH lone pair with CHCl2. Okay. So notice this structure, we have RNH with CH, Cl and Cl. So the lone pair keep pushing till the halogens keep removing out. So again we'll get RNH plus with double bond CHCl, and which will be treated out with OH minus, taking away this H plus. That will give you again RN double bond CHCl. Again, the lone pair will push it to remove chloride out. That's when we'll get this as RN triple bond CH plus. Okay, to which OH minus will take away this H plus, and that's how we'll end up getting RN triple bond C plus and minus, an isocyanate formation. So this is a typical mechanism how isocyanates are formed. Any kind of 1-degree amine will always give you this positive reaction. Any 1-degree amine gives positive carbyl amine test. Carbyl amine test. So please check this out quickly. If you have a doubt, please do ask. T, which can give positive carbyl amine test? Okay. Which amines give positive carbyl amine test? So it doesn't matter whether you have direct connection with benzene, even if it is crowded this this much, or like this, or whether you have a simple primary amine like this, correct? As long as they are primary amines, they all will give you carbyl amine test. So answer is all of them. So any kind of form we have, all of them will give positive carbyl amine test. Okay, so that means they all will form isocyanate and give foul smelling gas. Next, notice Reamer Tiemann reaction. Although this reaction is more familiar in phenols because it is a part of chloroform reaction, we are taking it here. Okay. So the reaction is mainly for phenols as they react with chloroform in the presence of NaOH to give this as O minus, Na plus and CHO, which on hydrolysis will give you OH and CHO, which is salicylaldehyde. So this is called salicylaldehyde formation. So to make a salicylaldehyde formation, this is the reaction that is being used. So let's see the mechanism one by one, step by step. How does this happen? First, CHCl3 plus NaOH will have a similar reaction. Once again, Chloroform, when you react with NaOH, we know that, okay, so check. First, we will get a carbene as usual. So we'll get this as CCl2, I mean CCH3 minus, and H2O will go away. And that will convert into CCl2 plus Cl minus, as we checked earlier in the carbylamine test. So this reaction is a common one, okay? And then phenol also becomes extremely activating ring in the presence of basic medium by converting itself into phenoxide O minus Na plus. So now that makes it highly activated ring. And such highly activated ring will definitely help in making an electrophilic attack now. So if you have O minus, we will have CCl2. So this is an empty orbital, so it is an electrophilic group. So pi bond will go and attack here. Okay. So let me write down this pi bond in this manner so that it is easy to learn. Right. So pi bond attacks here. So as it attacks here, we can get this as O minus with plus here and CCl2 minus. H is present here, double bond and double bond here. Of course, that minus and plus will become double bond O here, like this. And you know that CCl2 minus is here and H is here. Internally, this minus will take away this H plus, and this will try to push to bring back the aromaticity. And hence, we will get this as O minus and double bonds here, and you'll get CHCl2. Very important intermediate. So keep following, okay? So what are all the intermediates which are following? So this is one first intermediate which you will get. And now notice this intermediate O minus has a chance to push away the chlorides which are present here. So what will it do? It will push the electrons here. Pi bond will be pushed outside to remove one chlorine. That way, you will get again a double bond O here with double bond CH with one more Cl, and like this. This is also an intermediate, everybody. So the questions will be asked like this: which are the following are the intermediates in the Riemann-Tiemann reactions? So you should be able to figure it out. And then following that, if you have OH minus, see, OH minus can take away this H plus here. So let me rewrite this part as Cl and H here, like this. Okay. So OH minus as a nucleophile can attack on this carbon, try to push the aromaticity back. So that will make it O minus double bond with CH having OH group and Cl. Okay, this would be minus. And since it is in basic medium, this is the third intermediate, by the way. This OH minus will take H plus from the OH here, and we shall get this as O minus with CH, O minus and Cl. So within the molecule, if you have O minus and Cl together, they will immediately push to remove this chloride out. And as the chlorine goes away, you will get this into an aldehyde form. So you'll get this as O minus and CH double bond O. And as you get this, you hydrolyze it at the end, and that will convert into salicylic aldehyde. H3O plus, it will become salicylaldehyde. So OH with CHO, salicylaldehyde. Okay. So please remember the intermediates carefully. I'll just mark them. Okay. So first intermediate is this one. This is first intermediate. How does it look like? Please check it out. And then we have second intermediate here. This one, correct? And then we have this one, third intermediate. This is how it is forming. Clear? And this one is also an intermediate before hydrolysis. So please check. Anything could be asked. Which of these following are the intermediates present? So check this out. Please check the reaction, everyone. For Riemann-Tiemann to happen, we need to have a active aromatic group. So if you check out pyrrole is also a highly activating ring because of aromaticity. This will have sufficient aromaticity, and this when you react with CHCl3 in the presence of NaOH or KOH. Clear? Now this will give you two different products. One is called a regular Riemann-Tiemann reaction, where we expect aldehyde to form on this position. And second thing you will get is an uh, pyridine form with chlorine at beta position. So we'll get beta chloropyridine. Now the product which you are getting as beta chloropyridine, that is called abnormal Riemann-Tiemann reaction. Riemann-Tiemann. So abnormal Riemann-Tiemann as in instead of getting the normal aldehydes, we will get something new. Correct? So this is via Riemann-Tiemann. Riemann-Tiemann reaction. So one is via abnormal, the other one is via Riemann-Tiemann. So if you compare the major and minor product, this one is still major and this one is minor. But now let us understand how this minor product is actually forming. See, along with going for uh, substitution, you would notice that the aromaticity of pyrrole is not as strong as that of benzene. Hence, when you have CCl2 approaching, as the pi bond attacks here, the lone pair present on carbon can attack back and try to give more addition product than substitution. And that's what you will notice here. So first this pi bond, and then it will have connection with Cl and Cl, and this is how it will happen. So an addition product is favorable here. Addition product. But problem with this product is it is unstable because of the three-member ring form here. That helps in pushing this bond to make a double bond, and so does the ring will expand, and a chlorine will also leave from here. So hence you will see a six-membered ring forming here with nitrogen double bond, sorry, nitrogen adjacent to that we have double bond, and a new double bond has formed with C H and a positive position here. Okay, so OH minus will take away this H plus and retain the aromaticity and convert that into a pyridine form here. Hence, we will get like this double bond, double bond, double bond, and chlorine. So this is a product formation. Clear? So please check it out once quickly. Clear? So this is that abnormal Riemann-Tiemann reaction. Now, notice another case here. Suppose if it was given this way, without nitrogen, cyclopentadiene. This is cyclopentadiene. And that if you react with CHCl3 in the presence of KOH, okay, in that case, we will get chlorobenzene. Okay. Again, here the same thing can be expected first when the carbene is forming CCl2, correct? So you will notice the pi bond will take pi bond will attack to make its addition product here, like C, Cl and Cl, like this, and then this bond will be pushed here, and that will make a six-membered ring like this, correct? With double bond here, having chlorine here. Got it? And here there is a hydrogen, and you get positive charge. So OH minus will take up this H plus and push this bond to make the aromatic ring. Thus, you will end up getting chlorobenzene here. So this is a product formation. This is also an abnormal type. Okay, so chloroform has these 3-4 important reactions that could be asked in any subsequent chapters. So you learn to use it properly. A carbene formation and addition or substitution. This is a very typical cases of chloroform here. Okay, next. This was reaction. Did I number it anything? No. Let's put this asterisk again. So next reaction is about chloroform when you react with Cl2. This will only get oxidized to get CCl4 plus HCl. Industrially, CCl4 is called as pyrene. It's called pyrene, used as fire extinguisher. Fire extinguisher. Yeah. Problem with this is CCl4. If you react with O2, okay, this will also become sorry, H2, not O2, H2O. This could also become phosgene gas and HCl. So this is poisonous gas. So therefore, avoid high concentration, for fire extinguisher. Okay. Next, this could also become a preparation of CCl4. In a way, these reactions are also becoming preparation for CCl4. Another standard reaction is you take CS2, react with 2 moles of Cl2, right? In the presence of AlCl3, it will do something like addition on that sulfurs and give you CCl4 plus S2Cl2. No mechanisms required. Just remember the reaction here. Okay. And if you have CHCl3, okay, CHCl3 with zinc and steam, zinc and steam, zinc in an excellent reducing agent, so that will convert everything into methane, okay, and HCl. Got it? And next, if you compare the boiling point order, you will see CHCl3, sorry, CH3Cl will have less boiling point than CH2Cl2, then CHCl3, then CCl4. So that means as the chlorine increases, the boiling point keeps increasing. Okay. So these are primarily what you need to know it from in polyhalogens, everybody. Okay. Now listen to this last things. Basically, I mean, few extra reactions. These are some extra reactions here. So first one, benzene plus HCl. If you treat with O2, it will convert into chlorobenzene in the presence of copper plus H2O. Correct? This is called Raschig reaction. Raschig reaction. Second one is hydrolysis. Hydrolysis of chloroform. Second one is hydrolysis of chloroform, which is CHCl3. If you hydrolyze it, H2O, in the presence of OH minus. So all the chlorines will be replaced. You will end up getting as HCO minus and Na plus. Or if you heat this further, that will convert into carbon monoxide gas plus H2O. Okay, on heating. Clear? Next. In case if you have RCCl3 that is been hydrolyzed, H2O and OH minus. So in that case, it will become RCOO minus. Okay. So I guess the hydrolysis case is also clear. Right. Now, last in environment, I mean, the uses wise, if you notice, there is one term that is being used, that is freons. Correct. Freons are, uh, fluoro, fluoro, fluorocarbons. Suppose if at all I have freon 1,1, which means there is one carbon and one fluorine, and rest all are chlorides. So that means CCl3F. Okay. So if I write this as freon 1,2, okay, or simply 1,2, sorry, freon 1,2, which means I have one carbon and two fluorines. So that is CCl2F2. If it is freon 1,3, which means one carbon and three fluorines, which makes it CF3Cl. And lastly, if it is freon 1,4, it is one carbon and four fluorines, which makes it CF4. Right? This is the typical uh, representation. Correct? Suppose if at all we replace some chlorines with fluorine, so this will become HFCFC. CFC, sorry, HCFCs. HCFCs. Okay, this is CFC. HCFC is something like CHCl and F2. Okay, so basically this is R. Now instead of freon 1,2, a shortcut is used industrially. It is R22. Okay, so that means carbon and hydrogen are two new atoms, so that will be 2 and 2, 2 for two fluorines. Okay, this R22 is used as coolant gas for refrigeration as well as in AC ducts. We'll notice that R22 is used. That's it. This is how much we need to learn it from this topic. So I hope you guys got an idea about how the uh, alkyl halides, aryl halides, and polyhalogens. Okay, we have covered almost every point which is required in this case. So I hope you guys got this right.